Okay, welcome to my next video for IB chemistry. Right now we're in Unit 5. So we're in Unit 5, that's basically thermochemistry. So we're doing the whole unit on thermochemistry, which basically has to do with the enthalpy changes, the entropy changes, the Gibbs free energy. And we've already kind of talked about the difference between heat and temperature, and basically how much heat can be added to a system. You know, it's proportional to the amount of substance we have. If we've got a lot of substance and you add a little bit of heat, we're not going to cause a big temperature change, right? That's like if we got a brick of copper versus a small amount of copper. You heat this for 10 minutes. You know, maybe the temperature change is going to be very small. You heat this for 10 minutes, maybe it's going to be red hot. So we got, differences between temperature and heat. Heat is how much energy is actually, heat is a unit of energy, whereas temperature is a unit of the average thermal energy contained within the substance. So basically today we're going to introduce an equation that we use to calculate basically the heat change of a reaction. So that equation that we're going to have is we're going to have Q, which is our heat, equals mc delta T. So Q is equal to heat. So it's a unit of energy, so you can imagine the units are going to be kilojoules or joules. M is equal to the mass, which we know our standard units are going to be grams or kilograms. We've got C, which is the specific heat capacity, which we're going to define that in a second. And delta T is equal to the change in temperature. So that's T final minus T initial. So what the specific heat capacity is the specific heat capacity C. Give me a second, I want to make sure the definition that I wrote down is the exact right one. It's the amount of heat, so that should tell you the units are going to be kilojoules or joules, needed to raise the temperature of 1 gram of substance by 1 Kelvin. So how much energy you need in order to raise a specific amount of substance, raise the temperature of a specific amount of substance by 1 Kelvin, by 1 K, 1 Kelvin. So to give you an example of this, right, let's just imagine, copper has a specific heat capacity of 0.385 joules. So that's our unit of heat, joules, per gram per Kelvin. So joules per gram per Kelvin. Whereas ethanol, ETOH, has a specific heat capacity of, where did I write it down? 2.44 joules per gram per Kelvin. So if how we can compare them, right? We can say we added in 50 joules of energy. Just give me a second while I get my calculator. I'll just open up the calculator app right here, actually. So if we basically take this, we added 50 joules of energy. So this takes 2.44 joules in order to increase 1 gram of substance, 1 1 Kelvin to increase the temperature. So if we imagine we added 50 joules of energy to copper and we've added 50 joules of energy to ETOH, and we want to know what is the change in temperature. What temperature change is this going to cause? So it only takes 0.38385 joules to raise the temperature by 1 degree Kelvin. So if we got 50 joules, we just do 50 divided by the specific heat capacity. So 50 divided by 0.385. We're going to raise that temperature by, let's just round this up to 130. We're going to raise this temperature by 130 Kelvin. We're going to do a 130 degree Kelvin increase. Whereas for the hydroxide, we do 50 divided by 2.44. We're going to get a 20.5. So we're going to increase the temperature by only 20.5 Kelvin. So this is just assuming that we only have 1 gram of substance. So we can see that, depending on the amount of heat we add, the substance is going to gain temperature a lot different, right? If we increase the amount of grams, of course, the temperature raise is going to decrease because you need to heat. It's just like basically heating, like I said, heating a giant brick versus a tiny little box. You heat this with a hot plate for 10 minutes, it's not going to cause a big change. Heat this with a hot plate, it's going to cause a massive change. So that's what the specific heat capacity is. The specific heat capacity just talks about how many joules you need to change, how many grams per Kelvin, or 1 degree Kelvin, or how many joules you need to change 1 gram of substance, change the temperature of 1 gram of substance. So how to use this equation is basically, this is going to be the tricky part, right? The specific heat capacity, I have to say, is going to be one of the trickier parts, because in your book and what you're going to see in IB, specific heat capacity is offered in 2 different units. It's either offered in joules, gram, Kelvin, or it's offered in kilojoules, kilograms, Kelvin. So you can see that they're a very similar thing, right? The kilos cancel off and you get joules per gram per Kelvin. But it depends on what unit we're going to use, right? Kilojoules, kilogram, Kelvin. So this tells you what units you have to use, right? So if the question gives you a specific heat capacity in joules per gram Kelvin, you know that your mass, you need to supply it in grams. Your temperature, you need to give in Kelvin. And then your energy unit is going to be in joules. Energy, basically our Q is going to be in joules. And we can convert that to kilojoules if we wanted to. Whereas right here, right, it tells you what the question needs your units to be in. So it's just like in physics, right? You need to cancel a few things off. I need to just plug in my headset. Give me 1 second to plug this in, and I'll be right back. Okay, we're good. So the units of C tell you what you need to have what you need to do your calculations. So let's practice with a few of these calculations. So basically, if you saw from your textbook, they have a nice work through, and I'm going to talk about it. So let's just say we've got 1.15 grams lithium chloride. So this is from your book. You can also read through it in there, but I want to kind of define it for you. You dissolve 1.15 grams of lithium chloride in 25 grams of H2O. Okay? The temperature change is 3.80 Kelvin. And the question can ask you how much heat did it release? So so how much heat did the basically dissolution release? So if you can imagine it, right? We just got we've got the value that we care about, how much solution there is. We've got the temperature change, and what you guys are going to find for lots of these questions is C is given in your data booklet. So this type of question is usually a paper 2, paper 3 question. It's a long answer question, and C is given in your textbook. And C, the unit, is 4.18 kilojoules, kilograms, Kelvin, which is the same thing. C is the same thing as 4.18 joules, gram, Kelvin. Just because these kilos cancel up, a kilojoule, 1,000 joules, a kilogram, 1,000 grams. 1,000 divided by 1,000 is 1, so it's the exact same thing. So how much heat did this dissolution release? So if we were to calculate this, so let me change colors. I just realized I didn't change them at all in this. You write out your equation first. Q is equal to mc delta T. So Q is equal to the mass of what's going to change temperature, right? The lithium chloride is not going to change temperature, but the solution, the substrate, is going to change temperature. So we've got M, which is 25 grams, C, which, I'm dealing with grams now, so I should use this bottom one, which is 4.18 joules, gram, Kelvin, and our change in Kelvin is 3.80 Kelvin. So I've kept these units here so that we can know how our final unit's going to come out. So Q, if we do this calculation, Q is equal to 25 times 4.18. 25 times 4.18 gives you 104.5 multiplied by 3.8. Multiplied by 3.8. 3.80. So we've got 397.1. So Q is equal to 397.1 joules. Joules. So that's our unit in joules. If the question states that it wants the answer in kilojoules, you take this number and you divide it by 1,000. So Q is equal to, divide by 1,000, 1, 2, 3, 0.3971 kilojoules. So that is your answer. That is how much heat basically was absorbed or released in this case. How much heat was absorbed or released when dissolving lithium chloride through dissolving lithium chloride. What we saw is that we had a temperature increase, so we know that this much energy was released into solution. The solution got hotter, so therefore it was exothermic, which means that our heat released is negative. So we've released 397.1 joules, or we've added 397.1 joules to the system. So you can kind of think about it in either way you want, but in this case, Q should be kept positive. And then for our delta H, which is our next calculator, our change in enthalpy, which is our molar enthalpy change, takes into account whether it's released, whether it's endothermic or exothermic. So then how to do the next part of the equation. So I'm going to erase this right now. I'll erase this top part up here. So hopefully you remember the equation, or you've got the equation written down. If not, Q equals mc delta T, and hopefully you know that what the heat is mass, specific heat capacity delta T. So now it's going to ask, okay, if dissolving 1.15 grams of lithium caused this much of a temperature change, released this much heat, not a temperature change, released this much heat, how much does dissolving 1 mole cause? What's the temperature change there? So for that we need to look at our periodic table. So we go to it. See, lithium here is 6.94. So the molar mass of lithium chloride equals 6.94 plus chlorine, 35.45. 35.45. So the molar mass of lithium chloride is equal to 6.94. So it equals to 6.94. Oops, sorry. 6.94 plus 35.45, 42.39. So we've got 42.39 grams per mole. And we calculate how many moles we've already dissolved. So the molar mass, or not the molar mass, so to calculate the amount of moles, what we do is we do the grams of lithium divided by the molar mass. So 1.15 divided by 42.39 grams per mole. And this one is grams. And what that answer is that is 1.15 divided by 42.39, 0.027. So we've got 0.027 moles. So now if we were to calculate how many kilojoules, we want to calculate the enthalpy. And remember, the enthalpy, the units are kilojoules per mole. So if we were to calculate the enthalpy change, you just take what was the heat change, 0.3971 kilojoules, divided by how many moles, 0.027 moles. So that'll give us the same unit, right? That'll give us kilojoules per mole. So if we do this calculation, we'll have 0.3971 divided by 0.027, and we've got a delta H, an enthalpy change of 14.7, of 14.7 kilojoules per mole. And then now is where the part that comes in, the important part comes in. This is just talking about heat. We've heated the system by how much heat, and now we got to say whether it's going to be negative or positive. So since the system has increased in temperature, we've got a negative delta H value. Is that the reaction was exothermic. So okay, so hopefully this video was somewhat helpful, just to do the calculations, and just practice. If you practice these calculations, you do 10 of them right now. You just go online, do 10 of them, and you will be set. You will not have any trouble with this. In the next video, we're going to do a few more calculations and how to basically extract data from a graph. But one last point that you want to do here is that basically the lower the heat capacity, so we kind of already talked about this already. The lower the heat capacity, the less amount of heat is needed to cause a temperature change. So something with a very low specific heat capacity, a small amount of heat can cause a massive change in temperature, whereas a higher heat capacity, you need to add a lot of heat in order to cause a change in temperature. So hopefully this video was useful. Keep in contact with me, like I always say.